can derive the formula for speed of longitudinal wave or speed of sound wave through a medium. Sound wave travel in the form of compressions and rarefactions, and the speed of sound wave through a medium, it depends on bulk modulus of the medium, and it also depends on the density of the medium. So, speed of sound wave through a medium depends on bulk modulus and density of the medium. Bulk modulus represented by B and density of the medium represented by rho. And we can derive the formula for speed of sound wave using dimensional analysis. Okay. So, speed of sound wave, that is V, is directly proportional to bulk modulus raised to A and density raised to B. We can derive using dimensional analysis. Okay. So, first you can write the proportionality, then we can change the proportionality sign by a constant. So, V equal to a constant K, B raised to A, rho raised to B. We can apply dimensions, applying dimensions, velocity L t raised to minus 1, that is the formula for velocity. Then K, it is a constant, no dimension. Bulk modulus its dimension is same as that of pressure, and its dimension is m L raised to minus 1 t raised to minus 2, that is the dimension of bulk modulus of pressure. Density, that is mass by volume, so m L raised to minus 3 the whole raised to B. Here we can put whole raised to A. We can take the m terms together, so m raised to here A plus B, then L raised to minus A, here minus 3B, then T raised to minus 2A, okay, T raised to minus 2A, here LT raised to minus 1. We can equate the powers of mass, length and time. Now we can equate the powers of mass. Here A plus B is equal to 0. Equating the powers of length, minus A minus 3B is equal to 1. Then equating the powers of time, here minus 2A is equal to minus 1. Okay. Equating the powers of mass, A plus B equal to 0. Then equating the powers of length, minus A minus 3B equal to 1. Equating the powers of time, minus 2A is equal to minus 1. So, using that we can write here A is equal to 1 by 2. Then here if you substitute in this formula, A plus B is equal to 0, A equal to 1 by 2, no? So, B is equal to minus 1 by 2. So, A equal to 1 by 2, B equal to minus 1 by 2. We can substitute in this equation. Here velocity V equal to K B raised to A. What is A here? 1 by 2. Rho raised to B. B is equal to minus 1 by 2, or V equal to K into root of B divided by rho. Here the constant K is equal to 1. K equal to 1. Therefore, velocity V equal to root of B divided by rho. So, velocity of longitudinal wave or velocity of sound wave through a medium is V equal to root of B divided by rho. Okay, children. Now, I can see what is the speed of longitudinal wave in a solid bar. We know velocity of longitudinal wave in a medium is given by V equal to root of B by rho. And here in a solid bar, instead of B we can put Young's modulus. So, instead of B we can put Young's modulus. So, therefore, here B is equal to, or B can be substituted as Y. So, instead of B we can take, we can take Young's modulus Y. So, here V is equal to velocity V equal to root of Y divided by rho. So, in the solid bar, velocity of sound wave or velocity of longitudinal wave is equal to V equal to root of Y divided by rho. Now, for solids and liquids generally have a higher speed of sound than in gases. So, speed of sound is maximum through solids and liquids. This is because liquids and solids have high value of bulk modulus. So, bulk modulus is maximum for solids and liquids, and hence velocity is greater for solids and the liquids. The speed of longitudinal wave in an ideal gas is given by V equal to root of P by rho. Instead of bulk modulus or instead of Young's modulus, substitute pressure P. So, velocity V in an ideal gas is given by root of P divided by rho. And this relation was first given by Newton, and hence it is known as Newton's formula. If you see the question, estimate the speed of sound in air at the standard temperature and pressure. The mass of 1 mole of air is 29 into 10 raised to 3 kilogram. And we know 1 mole of gas occupies 22.4 liter at standard atmospheric pressure at STP. We know 1 mole of gas occupies 22.4 liter at standard temperature and pressure. And we know density is equal to mass by volume. Okay, mass is 29 into 10 raised to 3 kilogram and volume is 22.4 liter. It is converted to meter cube. So 22.4 into 10 raised to minus 3 meter cube. Okay, so this represents the density, mass by volume. And if you simplify, the answer is 1.29 kilogram per meter cube. So density is mass by volume, and we got the value as 1.29 kilogram per meter cube. And velocity, using the formula V equal to root of P by rho. This formula, root of pressure, atmospheric pressure is 1.01 into 10 raised to 5 Newton per meter square. Okay, so this is the atmospheric pressure divided by density is 1.29. And if you simplify, the answer is 280 meter per second. So if you substitute the formula V equal to root of P by rho, pressure is atmospheric pressure 1.01 into 10 raised to 5 divided by density is 1.29, and you will get the answer as 280 meter per second. Okay, but this result is about 15% smaller compared to the experimental value of velocity. We know the experimental value of velocity is, speed of sound in ideal gas is 331 meter per second. Okay, so this is the experimental value of velocity, that is 331 meter per second, and using the formula V equal to root of P by rho, we got the answer as 280 meter per second. So that is not equal, or that is the theoretical value, that using the formula we got the value, and it is much smaller, 15% smaller than the experimental value. Hence this result shows that theoretical value, which is 280 meter per second, is about 15% smaller than the experimental value, that is 331 meter per second. Hence from the above example, we found that there is some error in Newton's formula. The reason for this discrepancy can be traced when we examine the basic assumption on which Newton's formula is based. So Newton assumed that when sound propagates through the medium, the pressure variations are isothermal. Okay, that was his assumption. So when sound propagates through a medium, the pressure variations are isothermal. Based on the assumption, he derived the formula as V equal to root of P by rho. But Laplace, another scientist, Laplace was the first to question this assumption. Laplace was the first to question this assumption. He pointed out that when sound propagates through the medium, when longitudinal wave propagates through the medium, the pressure variations are not isothermal, but it should be adiabatic. Isothermal means temperature remains constant. So as Newton assumed that when sound propagates through the medium, pressure variations are isothermal. That means temperature should be a constant. And Laplace pointed out that the pressure variations cannot be isothermal, it should be adiabatic. Adiabatic means heat, no heat is absorbed or no heat is rejected. Okay, it should be adiabatic. And hence Laplace corrected the formula as velocity V equals gamma P divided by rho. Okay, he put a term gamma also, and gamma, we know gamma is equal to Cp by Cv, that you know. What is Cp? Cp is the specific heat capacity at constant pressure. What is Cv? Molar specific capacity at constant volume. So he introduced the term gamma in Newton's formula. He corrected Newton's formula as V equal to root of gamma P divided by rho, and gamma is the ratio of molar specific heat capacities. And this modification of Newton's formula is referred to as Laplace correction. Hence the modification of Newton's formula is referred to as Laplace correction. So Newton's formula is V equal to root of P by rho, and Laplace correction is V equal to root of gamma P by rho, where gamma is called the ratio of the specific heat Cp divided by Cv. Now we can check whether this equation is correct or not. For that, for air, gamma is equal to 7 by 5. The ratio of specific heat capacities for air, gamma equal to 7 by 5. And now using the Laplace correction, V equal to root of gamma P by rho, the speed of sound in air at STP is found to be 331.3 meter per second. Okay, so using the formula, the velocity of sound in air is 331.3 meter per second, which perfectly agrees with the experimental value. Okay, the experimental value is 331 meter per second, and using the Laplace correction, we got the value as 331.3 meter per second. So both the values are perfectly correct, and hence Laplace correction is in agreement with the experimental value. Now we can do a numerical. At room temperature and pressure, 4 gram of helium occupies a volume 22.4 liter. Gamma, the ratio of the specific heat of helium, is 1.67. Find the speed of sound in helium. Okay, so what are the values given? Mass is 4 gram. Solution, mass is equal to 4 gram. We can convert it to kilogram. So 4 into 10 raised to minus 3 kilogram. Now volume is 22.4 liter. We can convert to meter cube, that is 22.4 into 10 raised to minus 3 meter cube, that is volume. Now gamma, what is the value of gamma? Gamma equal to 1.67 given. And we know pressure. What is the pressure? Atmosphere pressure is 1.01 into 10 raised to 5 Newton per meter square. So these are the values we know. We know speed of sound in helium is root of gamma P divided by rho. Dear children, is equal to, we can substitute gamma. Gamma is, what is gamma? 1.67 into pressure 1.01 into 10 raised to 5 divided by density. Density means mass by volume. Mass by volume, no? So here it is 4 into 10 raised to minus 3 by volume. Volume is this one. That comes to the numerator, that is 22.4 into 10 raised to minus 3. Okay, we can substitute. Gamma is 1.67, pressure is 1.01 into 10 raised to 5 divided by density. Density means mass by volume. 4 into 10 raised to minus 3 divided by 22.4 into 10 raised to minus 3. And after simplification, you will get the answer as 970 meter per second. Okay, so using the Laplace correction, V equal to root of gamma P by rho, we will get the answer of speed of sound in helium as 970 meter per second. Okay children. Now we are going to discuss about a very important topic, the principle of superposition of waves. When two waves superpose or overlap, the resultant displacement is the algebraic sum of displacements of each wave. This principle is called the principle of superposition of waves. So when two waves, when they superpose means when they combine together, the resultant displacement is the algebraic sum of displacements of each wave, and this is called superposition of waves, and this is the principle of superposition of wave is the basic to the phenomenon of interference. So interference is a very important phenomenon shown by light and sound waves, and the interference of light we will study in the 12th standard. So superposition of waves is the basic to the phenomenon of interference. Consider two travelling waves on a stretched string. Let both with same wavelength, angular frequency and angular wave number. Okay, so consider two travelling waves travelling on a stretched string, and both the waves have same frequency, angular frequency, wave number, wavelength, and also the wave speeds are also same. And let the waves are travelling along the positive x direction, and there is only change in the phase constant or phase initial phase phi. So waves only differ in their initial phase phi. Let the two waves are y1 equal to a sin kx minus omega t, and the second wave is y2 equal to a sin kx minus omega t plus phi. Okay, so these are the two travelling waves. First one a sin kx minus omega t, and the second one is a sin kx minus omega t plus phi. That means they have same value of angular wave number, angular frequency remains same, amplitude is same, and they are traveling along the positive x direction. And there is only one difference is here the phase difference is phi. Okay, so initial phase is phi. Phase difference is between the two waves, the phase difference is phi. When they superpose each other means when they cross each other, when they combine each other, according to the superposition principle, net displacement is y equals y1 plus y2. Okay, the total displacement, the net displacement is the algebraic sum of individual displacements or displacement of each wave. So, y equal to y1 plus y2, and y1 we can substitute a sin kx minus omega t plus a sin kx minus omega t plus phi. From this a can be taken outside. So, a into sin kx minus omega t plus sin kx minus omega t plus phi. And we can find out the result by using the trigonometric function. We have what is sin A plus sin B. This is of the form sin A plus sin B. We have sin A plus sin B equal to 2 cos A minus B by 2, A minus B by 2 cos A plus by B by 2. Okay, so this is the trigonometric identity. So, sin A plus sin B is 2 cos A minus B by 2 cos A plus B by 2. So, using this relation we can write y equal to 2 cos, okay, 2 cos. So, here 2a cos A plus B by A minus B by 2, let this is A, here this is B, A minus B by 2. A minus B by 2 means here kx minus omega t plus phi minus kx minus omega t. Okay, so after simplification you will get cos phi by 2, all other value get cancelled. Then cos A plus B by 2, this value kx minus omega t plus phi plus kx minus omega t. So, it is cos 2 kx minus 2 omega t plus phi by 2. Okay, so using this trigonometric identity, we can write y equals 2a cos phi by 2 cos 2 kx minus 2 omega t plus phi by 2. So, that can also be written as 2a cos phi by 2 cos, here 2 can be taken common and cancelling. So, here it becomes kx minus omega t plus phi by 2. Clear, children? So, the resultant displacement is given by when the two waves travelling along the positive x direction, when they superimpose, resultant displacement is 2a cos phi by 2 cos kx minus omega t plus phi by 2. And this equation shows that the resultant wave is also a travelling wave, travelling along the positive x direction with same frequency, wavelength, angular frequency, etc. So, resultant wave also has the same value of angular frequency, same value of angular wave number, and the same wavelength also. Okay, and it is also travelling along the positive x direction. Therefore, the resultant wave is also a travelling wave, travelling along the positive x direction with same wavelength, angular frequency, and angular wave number. Thus, we know when two waves superimposed each other, the resultant wave is y equal 2a cos phi by 2 cos kx minus omega t plus phi by 2. So, here what is the amplitude? Amplitude is 2a cos phi by 2 represents the amplitude. What is the amplitude of each wave? Amplitude of the first wave is a. Amplitude of the second wave is also a, and the resultant amplitude is, what is the resultant amplitude? When they superimpose each other, the resultant amplitude is 2a cos phi by 2. Therefore, the resultant amplitude is a dash. We can write the resultant amplitude of the resultant wave is a dash equal to 2a cos phi by 2, where phi represents the phase difference between the two waves. We can see the two cases. Case 1, first case, if phase difference phi equal to 0, phase difference 0 means like this. This is the first wave, and here this represents a second wave. Okay, children, these are the two waves. So these are the two waves. This is the first wave and second wave, both having same amplitude, both having same frequency, wavelength, angular wavelength, number, etc. So when they superimpose, that means if phi equal to 0, phi equal to 0 means they are in phase. Phi equal to 0 means the two waves are in phase, have the same phase. So here it starts from 0 like this, start from 0 and increases. Here also it starts from 0 and increase. That means the two waves are in phase. So that means phi phase difference is equal to 0. Phi equal to 0 means there is no phase difference, that means the two waves are in phase. If phi equal to 0, we can write, if phi equal to 0, what is a dash equal to, what is the value of a dash equal to phi 0, cos 0 is 1. So here we can write 2a cos 0 and it is a dash is equal to 2a. So when the two waves having amplitude a each, the amplitude of this wave is a, amplitude of the second wave is also a, when they superimpose, the resultant wave amplitude is 2a, it doubles, amplitude doubles. Okay, so how will you represent the resultant wave? Resultant wave can be represented like this. Amplitude doubles. So amplitude double means the amplitude increases like this. Okay children, so here the first wave having amplitude A, this is the amplitude here, the first wave having amplitude A, second wave having amplitude A, but the resultant wave having amplitude, what is the amplitude? Doubles to A. So when two waves having amplitude A, when they superimpose, when they combine together, if they are in phase, what is the resultant amplitude? Resultant amplitude doubles, so amplitude increases. And this type of interference is called a constructive interference. So this type of superposition or interference is called a constructive interference, where amplitude increases, amplitude becomes maximum. Now we can discuss case 2. Again we know amplitude of the resultant wave is a dash equal to 2a cos phi by 2. Case 2, if phi equal to pi, phi, the phase difference phi equal to pi, that means the two waves having a phase difference pi, the angle between them is pi, like this. This is the first wave and this is the second wave, both having phase difference pi. So first wave starts from 0, it becomes maximum, then decreases like this, and the second wave starts from 0 and it moves in the opposite direction. So what is the phase difference between the two waves? Phase difference is pi. Okay. Now what is a dash? A dash can be written as the resultant wave a dash is, when they combine together, the resultant wave a dash is here. We can substitute pi, phi equal to pi. So the resultant amplitude is 2a cos pi by 2. Cos pi by 2, cos 90 degrees 0. So what is a dash? A dash equal to 0. Okay, so when the two waves having phase difference pi between them, amplitude is equal to 0. That means no wave is produced, and that is called a destructive interference. If amplitude becomes 0, and that interference or that superposition is called destructive interference. When two waves having phase difference pi and amplitude is equal to 0, the resultant amplitude is equal to 0, and that is called destructive interference. Amplitude is 0 means no wave is produced. So how will you represent the resultant wave? This is the resultant wave. Amplitude is equal to 0. So resultant wave is 0. Okay, so this one crust, this is called a crust. Here this is called a trough. Crust and trough combines together, amplitude 0. Here also trough and crust combines together, again amplitude is equal to 0. Okay children, so when two waves having the phase difference 0, that is in the first case, two waves having phase difference 0, that means the two waves are in phase, amplitude doubles, and that is called a constructive interference. And when two waves having phase difference pi, amplitude, resultant amplitude is equal to 0, and that is called a destructive interference. Here this represents constructive interference where amplitude is maximum, and destructive interference where amplitude is 0.